Yeah, good evening. So we come to a live session of 12th week. So this week is all about that nonlinear functions and how we are describing these nonlinear functions, and if we have a nonlinearity in the system, then how we are going to model the system, and what are the problems which we come across due to these non-linearities. So if you see that input-output relation, how these non-linearities affects the system performance, that is the one thing. And second thing is all about, so this is a very small session, and if we see, if you want to see that previous, whatever the current assignment questions, so we'll take some sort of the questions from that, and I will be covering some from assignment 3, assignment 2, assignment 1, whatever is possible. So I will consider those assignment questions and we'll see if anybody asks. So then we'll try to solve those questions. So other than this, one more thing, uh, we'll take we have one more session, that is tomorrow, Sunday, I think. That's scheduled to be Sunday, so you will get an announcement on this. And then after, so we'll see all these sort of assignment questions which we have already, current assignment questions we can discuss. And today we try to discuss about some assignment 2 and 3. We'll see that. So I will try the best questions, like very tough questions, and we'll try to solve that questions. Okay, so let's wait for 2 to 3 minutes. So if anyone joins, then we'll see. So draw the basic nonlinear signals of this. So one is related to quantization, hysteresis, and saturation, and the meaning of Z zone. So draw that four different type of nonlinearities which are present in the systems. Normally, these nonlinearities we frequently come across, right? So far whatever we have gone through, that is only linear systems, but now these type of effects, you can see quantization, hysteresis, saturation, dead zone, and all these things we can have, these frequently comes in the system. So now how it affects the performance, that is all different case, but now just draw the each signal and try to know it by that uh, quantization and what perspective comes, hysteresis. Yeah, take time. Okay, so normally quantization is all about is like if you see where there is a link between analog signal to discrete signal. So now if you see analog link is all about what you will convert analog signal to digital signal, that is all ADC can do that. So when you are converting that, so what actually happens, so ADC is having its clock and it is being sampled at uh, some particular frequency, some megahertz, you can say that. So normally you have a, now you have a some sort of the signal having this manner like this. Now that clock, each sample is being taken at some frequency, you can say that this is a sampling frequency, f sample. Okay, so now if you see, observe this is actually having a continuous signal. So now the quantization, what this will do, this will take a sample of each particular time interval at this point only. So at this point what we have a sample. The sample value you can take it as a some a1, this is a2 and a3. So now if you see this a1 value will be somewhat here till this, until next sample comes it will have the whole value same. So this is a2 and this is a3, and if you see this one, and again it is less. So if keep on going, it is having a sampler, right? It is sampling the value. So now the waveform is discretized. This is called you can say the sampling of this one. But now if you see this, suppose you have a sampling, suppose you have a 10-bit ADC, so that is having resolution of 2 power 10. That means the minimum value which can produce by this one is only this much. Now if you have a 2 power 8, it will be even lesser. So that means it can able to give only this much value, minimum resolution. Okay, so now this value to this value, so what is it? It is called, you can say that quantization. So we are missing that actual value, so it is trying to hold that value. So this is all about that quantization effect. So normally in practical what we do, we don't use that analog control because we have a such advanced discrete DSP processor, digital signal processor, or FPGA, and because of all this, its implementation of the controller in the processor is so easy. So that in if you talk about analog control, that is analog control is all about um, making that op-amp circuits, trying to that analog control, right? So that developing that operational amplifier circuit, that signal conditioning circuit, with all non-linearities, considering all non-linearities, like it's quite difficult, it's very very difficult. So it's better as much as we can reduce of it, that signal conditioning circuit, so that the controller implementation, of this controller is quite easy in this DSP. Okay, because these are operating at very high switching frequencies, so it's not an issue. So that is all about the context. And whatever the hysteresis is about a certain band, it will not respond. So you can see this type of bands. So this is called hysteresis band. So normally this also comes under the nonlinearity. And what about this saturation? Suppose saturation is all about, so you have an operational amplifier circuit, so that operational amplifier circuit, you are using it for comparator. So this is one signal, this is you can take, this is V plus and this is V minus. So you are giving that VCC here plus VCC, and this is minus VCC. So what you are doing, suppose you are comparing some sorts of sine signals with the triangle signal, triangle signal. So what exactly you consider, this is a comparator, right? So if this signal is more than this signal, so it will get the PWM signal. So what you can say that it is just like a sine PWM. So what it exactly does, now when you're operating this one, it will give either plus VCC or minus VCC, right? So this is all about that, because this operational amplifier we are intended to operate in the saturation region. So if it is less than that, suppose if this value is some 10 millivolts, suppose this is I am giving as a 10 millivolts and this is its 2 millivolts. So the difference is 8 millivolts, right? So it is less than, suppose this is a like plus 5 and minus VCC is 0, so suppose, yeah, minus 5, so it is less than this one, so it is giving it. Suppose this is a 5 volts and this is 0 volts, so it is very close to the saturation, so it will also give the 5 volts. But if this is 6 volts and this is giving a, you know, is also, you know, minus 1 volt, now what happens, what is the difference, it is 7 volts, so that it is positive in quantity, so definitely it will not give that 7 volts. So what it will give, it will give maximum this, so that means op amp is under saturation. So normally saturation is all about that. So if you talk about that, we are operating this operational amplifier in this linear zone till whatever the value, still less than VCC, plus VCC and minus VCC. If it is the value, the difference of output, if output is start crossing the plus VCC or minus VCC, it will be saturating. So this is the thing. So but our designs, whatever we do, we develop the design circuits which intended to operate the any of the system to within this zone, so linear zone. So we avoid it, these things, because during non-linearity, so we cannot expect to be a system response as we are desired. So that is the one thing. Next thing is a dead zone. Dead zone is all about that the system doesn't respond for small entity, small time duration. So that means you wanted to get a some change of it. Suppose you have a some sort of system, suppose you have a id sorry, you have some reference value and this is an actual value. So you are passing through this one at controller, so that you can say that C of S. And because normally discrete systems will offer that it is a Z inverse, so that means you are giving some unit delay, so that unit delay is all about that the amount of time which you are giving it. So this you can say that C of Z, so there is a link. So this is again it is a plant P of S. So now from here you have an some ADC, you are converting into analog to digital, you are sensing that actual. So now if you see this is entire system which you are doing here is all about that discrete, right? So it is all about the discrete system. So now if we observe that in above, so what is actually happening, we are sampling at some frequency, right? We are taking the sample value at each one particular frequency, but when we are taking it, so first the loop will run for, we are taking one value of it, suppose you can say that fs, that n equals to 1 at n at the discrete point. So till that the entire value will be updated, computed, and it will giving to the plant, right? When next value comes, so before updating it, what is there, so already we have that previous value. So this value now, if you observe that one, there is a delay between these two, right? Suppose you want to give that any change here, it will respond after one unit delay only. Okay, so that will be a dead zone, we can normally say that. It is equivalent to be that, like you can say simple, the system will not at all respond, then after that only it will respond. So this we call as a dead zone, right? So if you see that, you know, diode characteristics, what will happen if the diode forward bias voltage, if apply voltage across the diode is more than 0.7, then only it will conduct. So that 0 to, if less than 0.7, it will not conduct. That is the point we say that dead zone. Okay, so these are all the basic non-linearities which we frequently observe in the systems. So yeah, so other than this we have you know, uh, different non-linearities, like um, um, signal multiplications, right? So, but normally, which we can see that frequently all these four are very common. Okay, any system can obey these things. So try to solve the question number 2. See the most appropriate, yeah. Suppose you have a basic system, consider that basic system, right? So among that basic system, like you have a simple plant here. C of S, this is P of S, Y of S, this is a reference signal, and this is an actual signal. So consider this base star. So the reference signal is nothing but sine omega t, a sine omega t. Okay, so now if this plant, just a minute, హలో, ఇక్కడనే రూమ్లో ఉన్న, పని మీద ఉన్న, పిఎంఆర్ఎఫ్ టీఏ వర్క్ మీద. ఆ? ఎందుకు? ఏ అదే అదేలే సార్. సరే సరే సరేలే, నేను ఇచ్చేది ఏం లేదు ఆడ. ఉమ్, 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 ఉమ్. సరే 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 సరే. Yeah, so now if you see this, um, so you have a system is non-linear system. So in this non-linear system, what actually happens? You try to find it out. See, choose the best option among these three. If you observe the first one, the sweeping the frequency of a sinusoidal signal, we can determine the frequency after which. It is just like, it is a linear system. You have a system, or whatever the analysis we have done, like, Nyquist stability and the Bode, all these things, what is all about? It is the gain and frequency plot over a frequency, right? So we can see the system stability for a different frequency. So we can observe that at what frequencies, uh, of, so we can see that system's stability with frequencies omega gc and omega pc. It is a generalized statement. So it is you can say that it is a linear system, right? Now, non-linear system, suppose if you say system is non-linear, you are giving input is sine omega t, so output should be expected what? If the system is linear, output should also be a linear system, sorry, that sinusoidal. Suppose if you see this r of s, so c into p by 1 plus cp, right? Sorry, y of s, right? So y of s into r of s. So c into p is all about what? If you want to see this is a magnitude, right? So magnitude, you can consider this is a transmission system. So what you can say, magnitude of t at an angle of t into r of, that will give, right? It will give some margin, magnitude and its angle, right, phase at that particular frequencies. So now if you have a non-linear system, so what actually happens? So any type of non-linear, so this will not obey, because suppose you have a such type of system, suppose you consider that is all about saturation, suppose saturation is an issue, so you have a some sort of signal. So this is an input signal, this we are passing this one to be certain, you know to a system having non-linearity. So saturation is all about what? You expect some phase delay, suppose if the system is offering it, so it will be saturated. So again sine, it will be sine. So again this is also You are giving sinusoidal but not getting a sinusoidal. So this is also wrong option. So this also wrong and this is also wrong. If a system on the verge of its instability and slowly decaying it. So normally, yeah, before coming to this point, you see that last option, a nonlinear system behaves like a linear system for some. No, not at all. Just now we saw that. So this is also wrong. So now let's make that what is it? So if a system is on verge of instability and its response slowly decaying for sinusoidal. So instability and stability. So what do you mean by stability? Stability is all about if you give the bounded input, you should get the bounded output, right? Bounded input and bounded output. So that means now if you see the poles and pole zero plot of it, what exactly normally is system? If the poles is exactly on the right of sorry on the imaginary axis which are not repeating. So what exactly we say that this is a marginally stable, it's a just like stable, just stable, it's like edge of stability, right? Edge of stability or instability, anything just small change if it crosses then it will become unstable. Now what happens, see you have a here if you give the step input of it, so it will go under oscillations and sorry it will undergo certain oscillations because these are all, you know, if you say that this is 0 less than zeta less than 1, so you will have all oscillatory response, and if this is, you know, zeta greater than 1, you will have a no oscillations but it is having a steady output. Now if it comes here, the system response either what you can say, it will keep on rising, it will go the unbound, okay. So that is actually happens for the non-linear systems. When you talk about the non-linearity system, so now what actually happens, non-linear system, so it means you consider that saturation or anything else, so it will definitely clip and it will start decaying, right? So you can say that, you know, slowly decaying sinusoidals. So that is the one. Now look at the third option, third question. Take time. The response x of t of a nonlinear system to a sinusoidal input r of t is equals to a sin omega naught t, where omega naught is close to the gain crossover frequency. Okay, omega gc, whatever, is a periodic signal, right? So, however, input of the character in nonlinear system we consider only first harmonic component because what? Because so try to solve this. Yeah. Yes. You try to draw the body plot for this. Suppose you take any type of systems. So, assuming that having a gain crossover frequency, okay, just consider that as gain crossover frequency. So try to take as a some first order type of system. Check. Okay. Now let's take a system like this. Okay. Suppose you draw that magnitude plot of it. Suppose you have this is omega gc. Yeah. So now if you see this is nothing but the omega naught, very close to it. So what actually happens? Now you are passing a system with a response of like, now you see, suppose you have this is R of S, right? And you have your controller is considered to be linear, and but the plant is offering some non-linearities. So that output signal, you can say that is having a effect of some nonlinear. So definitely we don't expect to be having a sinusoidal. So the waveform is distorted here. You will get it other than sinusoidal. So suppose you have such type of signals. Suppose you have uh, like this you have. So if you make the harmonic analysis of it, what you will have that, you know, some sort of signal x of s is equals to sigma k equals to 1 to infinite 1 to, so it's ak e power jk omega naught into t. So this is a simple Fourier series. If you expand that, you will say cos omega naught t plus cos 2 omega. So is having that. So these are its coefficients. So it will offer that effect, right? Now you have some component about this. First, that's the first frequency. Now after this, any frequency you take it, what actually happens? These AK, A1, A2, A3, depending on that, that will give a some factor, right? So it is nothing but what? Attenuation factors. So it will give us some gain factor. So you are getting this type of signal in compared to that. So whatever you get this one factor, so that factor is all about that a function. So other than, so it is just like a, if you see this for a linear system, so the other factors or other frequency components are what? It's trying to get attenuation. Okay. So now you are making, this is a non-linear, but you are making into a different type of sign, so it is equal, each one is looking like in linear, right? So when you're making it, now after this omega naught, whatever the frequency is that is getting attenuated, because you see that is the system response like that, so it will be attenuated. So whatever the components you are getting it, those are the attenuated one. So if you observe that, see, higher harmonic components are rejected because of magnitudes are attenuated, right? Try to, is it right, this option? Let's see. And see, because their magnitudes are amplified, no, because see, it's negative dB, right? It's, suppose you can say minus 20. Minus 20 dB means what? It is minus 1. Is it minus 10? Sorry, it is minus 10, right? So it is minus 10. So it is like a, you know, is it minus 10? Yeah, it's 10 power minus 1. So 10 power minus 1 means is like a 0 0.1. So 0 0.1, it's a factor of 10. So it is getting attenuated by 1/10 of it. So you can say that it's not getting amplified. See, the higher order harmonics are rejected because their magnitudes are linearly depending on the, it's not necessary. It's not necessary, right? So because if you take some sort of the signals, might be, suppose if you have a some, suppose exact square signal, suppose you have this, what you can write, this one is average value is 0, then if you say some a, this is minus a, right? So you can take like a by n pi, right? So n sigma, sigma n omega naught t, right? If you talk about this fundamental is t naught, so t naught by 2, you will have this. So here, because the magnitudes are being exactly for n equals to 1 a by pi, n equals to 2 a by 2 pi, so anyway even harmonics are 0 here, but third, fifth and all will be equally, it's like a factor of 1 by 3. So what is this one is exactly saying, linearly dependent on the factor of, it's not necessary if it's other than this. Suppose I have waveform like this, some sort of this, so we cannot say that all time, so it is different. So this also wrong. Higher order harmonic magnitudes are linearly independent of the first one, it is also not, sometimes it will, sometimes not. So the right option is this, so because it is getting attenuated. Okay, so this is all about this question. So any doubts in this? Okay, try to solve the question number 4, then after that we move to some assignment questions in some questions which are already given in this current live sessions, right? We'll see that. See, the response of a nonlinear system uh, is given by a periodic signal x of t. So the further the sinusoidal input uh, describing function for the nonlinear system is given that, right? So it just looks like a Fourier transform. Identify the correct statement below which describes that. Okay, so try to think of it. You have some periodic output signal because for sine excitation, so the nonlinear of the system is given that response here. So 1 j by pi a integral 0 to 2 pi x of t e power 1 j theta d theta. So with respect to that, so what is the first thing you get from here? It is a combination of certain harmonic. So x of t is a signal, right? X of t is a signal. You are converting into its equivalent transformation. So what is it? This discrete for sorry, this Fourier transform is saying that it is a function of, see, it is a function of omega, right? So having it is a factor a. So how is it now when you make it? It's first converting into you have, this is a periodic signal. If you make the Fourier analysis of this one also, it is having a first order, um, um what you can say, first harmonic, second harmonic, third harmonic, all these things will be there depending on the symmetry. So anyway, that high frequency components is what is some, it's whatever the amplitudes which we get for high frequency components are some different factor, because it is in non-linear system. So we can't say that exactly in above question. What we have seen, we have just seen that uh, it is, higher order harmonic component, it might be, it's not exactly linearly related. So it's like a factor of 2, 3, 4, like that. It's not like that. So here, but first harmonic component, if you see from there, from this expression x of df of omega a, so it is just amplitude is directly, attenuated, right, by a factor of a. So it is 1 by a. So what is it? The first harmonic component of x of t is directly is the amplitude of the input signal. So you see that definitely it will come if you make sure of it, right? It will have the ratio. So if you see this, so this is not at all, and the maximum amplitude of this one is the input or no, because it is having a pi a, so it is not same. The ratio of input phase of output, it's also not, because phase, because of nonlinear system we cannot say that. So it is only from this relation we can see that the first harmonic definitely it will have that. So this is all about that last week 12. Now let me give the one question which is related to some Nyquist plot. So try to identify how many number of, what is the phase change, okay, that we can see. Okay, so you have a function f of s is equals to s square plus 9s plus 8. Okay, so the Nyquist plot of this, suppose you have some contour. So you mapped entire, so you have some contour, you have decided it. So that contour normally having this way, like this. Okay, so this is real part of s, this is imaginary part of s. Okay, so now we know that this is my, this is -3 and this is -6. So if you see this, now you have some dot here, that a pole. So sorry, not pole, it is just like, you are trying to map that how many number, right? So you need to identify the total phase change of that s, the dot which you placed here. So you can talk, this is s, So suppose you take it at this point A, so it is having some angle, so the rotation of this one is like this. Okay, now try to identify that phase change which is offering by of this function f of s. So for one revolution, how much? So just when you are, assume that you are on that point, you are walking along that path which is designated here f of s, sorry, that is plane contour, then based on that how much phase change you can get it for this function f of s. Okay, see f of s is having how many zeros? Sorry, this is 18, my mistake. Okay, so try to identify now perfectly. Yeah, any idea? Okay, see, now if we check f of s, what are the function it is? F of s can be written as what? S square plus 6s plus 3s plus 18, right? I can write this one as a s plus 3, s plus 6. You have two poles, two zeros, right? So one is at here, another one is at here. Now what is exactly seeing it? Now when you are walking along this path, this how much angle which is contributed by 3 minus 3, and how much angle which is contributed by this. So when you are walking s, so you can take this as s. So because we are taking real part of it, so this point when you're walking along this way, suppose in this way, so what is this? Now see, now if you make the angle for this with respect to this, so with respect to this, what is the angle which is contributing? See, now I started at this point, now s plus 3 will make almost 360 degrees, and again back to this, again another 360 degrees. So it is 4 pi because it is encircled by two things. So this is a one circle and this is a another path. So because of these two, then this s minus 3 contributing that two revolutions causes the 4 pi because it is anti-clockwise, right? Definitely. Now, what about this s minus 6? Because when you are walking along this path, this loop, so only s minus 3 is there, but there is no. So this one is looking like this entire one as a dot, right? So you can consider this one as a single loop. So this s minus 6 is enclosed by single loop. This is the one. So now your final conclusion is that s plus 3 will contribute angle f of s is what is 4 pi, and s plus 6 will contribute an angle of, for f of s is 2 pi. So both the loops are in rotating in same direction. So that net angle is all about what? Angle of f of s is what? Angle of f of s is equals to angle of s plus 3 plus angle of s plus 6. So it is 4, yeah, it is 4 pi plus 2 pi, it will give 6 pi. So this is all about the net angle which you are getting it. Clear? So if you have any other questions, okay, then we meet on Sunday for extra questions. We can solve in some other tutorial questions, right? Okay, then see you.